In this video, we'll look at examples of a new class of functions that we haven't really considered yet thus far. So up until now, all the functions that we've basically done anything with algebra or calculus have been examples of, oops, let's do this in black, algebraic functions. So this is a class of functions, and there are certain kinds within it. The first one that you're probably familiar with are all of the polynomial functions. And then anything that was a fraction of polynomials, so we called those rational functions, was in this class of algebraic. And then also anything that you could get using radicals. So for example, square root of x, the cube root of x, and so on. So these things and stuff that you could get from mixing them. So for example, if you had something like the cube root of x plus 7 divided by something like this, then in a way this is kind of a mix of the cube root function along with inside here we've got a fraction. Or you could, kind of mix it the other way. So for example, you could do something like the cube root of x plus the square root of x all divided by x squared minus 9, something like that. So any kind of combination that you could make by composing two of these things together, or dividing them, multiplying, that sort of stuff. So all of the things in this sort of group collectively we call algebraic. Now there are plenty of functions that are not algebraic, and those functions are called, so if they're not algebraic, they're called transcendental. And good examples of this would be all of the trig functions. And we'll talk about those later in the semester, but the ones that we're really interested in are called exponential functions. So let's try the eraser. Exponential functions. And to go with that, then they're sort of the opposite of the exponentials. They're inverses, and we call those logarithms. And so today we'll start by talking about the exponentials, and then later we'll talk about the logarithms. And then the last thing that we'll do is talk about how you do calculus with these two sets of functions. So today will be sort of purely algebraic. Okay, so we're going to concentrate now on the exponential ones. And what those things look like is a number to a variable. Okay, so example, something like 2 to the x. Now contrast that with something like x squared, which is a polynomial. The difference here is where the number and the exponent are. So here we have a constant base that's raised to different exponents, and here we have a variable base that gets raised to the same exponent. So these two things, although they both involve exponents per se, we call this one exponential and that one polynomial. Okay, so they don't have to be 2 to the x or specific numbers, and in fact a frequent one that we'll look at is e to the x, and where e is Euler's number, and that's like 2.7178, blah, blah, blah. And I'll show you guys in class where this number comes from. Okay, now what do the graphs of these things look like? Roughly speaking, they look exponential. May seem a little silly to say that. But so let's just take the 2 to the x, this guy here, and I'll graph it over here. So one basic fact that we need to know from algebra, of course, is that if you raise anything to the 0, you'll get 1. And if you raise anything to itself, you get itself. And then, so we could start graphing this by graphing dots. So for example, 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4, so it would be way the heck up here now. And then if we start to go in the negative direction, 2 to the minus first, well, remember what negative exponents mean. That means that we need to do a fraction where the 2 is raised to the first in the denominator, and that's just 1/2. So we get this, and then if I'll just draw in a couple more here. 2 to the minus 2 is a negative, or sorry, a quarter, and then 2 to the third would be 8, which is way up here. Okay, so I'll just put the dot up here anyway. And then the graph of this function is just to play connect the dots, and up you go. So these functions grow very, very, very quickly. Now, what we'll look at in just a second is what happens if you change either what the exponent looks like or what the base looks like, and what kinds of transformations can we do on this graph. So the graphs of all of these exponential functions can be transformed basically in the same ways that we did the transformations before. So let's just take here, I'll sketch up just real quickly the same graph we had before, y equals 2 to the x, and so it looked something like this, and the special point here is 0, 1. So the so this was y equals 2 to the x. So if I start modifying this a little bit, oops, I'll do this, the axes in black. If we start modifying the function a little bit, so for example, if I did 2 to the something different than just a plain x, then what would that do to the graph? So for example, let's say that I did y equals 2 to the minus x. So based on what we did when we did the transformations, we should know that the minus in front of the x, so this is kind of the inside, should reflect the graph in the horizontal direction, so about the y-axis. And so in order to draw the graph, we can just reflect this graph. And so it still will go through the point 0, 1. And that should make sense because negative 0 is the same as 0. But otherwise, the graph basically just goes in reverse. Okay? And we should mention, of course, by the way, that the x-axis here is actually an asymptote. So 2 to the minus 1,000 is really close to 0, but not actually quite equal to 0. Now, you could, if you wanted to, also think of this as 1 over 2 to the x, which is the same as 1/2 to the x. The negative exponent puts it down here, and then the reason that I can write this equals this is because, of course, 1 to the x is always 1, and 2 to the x is the 2 to the x down here. I personally prefer negative exponents a little bit better here, but sometimes you see this and just realize that they're basically the same thing. Okay, so we could do the same idea. This was a reflection, but we could do scales and shifts and all sort of that stuff too. So let's just look at a couple more of them here. So set of coordinate axes, and let's say that we've got a graph. So we'll sort of do this one in reverse. I'll start with the graph, and then we'll try and figure out what the equation is that goes with it. Okay, so the graph here that I'm going to work with goes in this basic shape, kind of like the red one, except the special point here has different coordinates. It'll be 0 and 1/4. Okay, so there's a lot of ways that we could imagine doing this. If we started with the 2 to the x, the only problem, of course, is that the 1 here needs to be a quarter. So let's just say that we tried to do something like to say, well, it looks like the graph of 2 to the x, but I want the 1 here to be a 1/4. So we might try, well, why don't we just divide this by 4? And geometrically, that would be equivalent to a vertical scaling factor. Now what I'll show you is that this is actually equivalent to a shift too, which is kind of funny. And so let's think about, does this make sense? Well, if you plug 0 in here, you get 1 for this part, and then multiply by a quarter, and you get a quarter. So this graph does go through this point, and probably has a shape something like this. But let's rewrite this another way. So be a little crafty here. I notice that 1/4 is the same as 2 to the minus 2, and I also have 2 to the x, and the rules of exponents tell me that if you've got bases the same, you add the exponents, and so I get 2 to the x minus 2. So this is equivalent to taking this graph and shifting it 2 units to the right. The minus 2 is why it goes to the right instead of the left. Yeah, so in this case, what I could have thought about as being a scaling factor, I could also think about as being a shift. So sometimes you can, sort of view it in 2 different ways. But the thing with exponentials that usually gives it away is this special point here, namely what happens when you plug in 0. Okay, so the exercises in the pre-class are relatively similar to this. One of the questions, you're given sort of several variations on graphs, either like this blue one or this green one, and then you're asked to come up with what the formula might be for that thing. So it should be pretty straightforward. And in class, we'll talk about what e to the x looks like. It's relatively similar. And then along with a little of the history as to where e to the x came from in the first place.